Before electricity took over, compressed air was a serious contender for moving energy over long distances. Engineers built entire networks to send power through pipes instead of wires, but it lost out. Electricity was more efficient, easier to scale, and it quickly spread across countries. Compressed air faded into niche uses, but now it's coming back, buried hundreds of meters underground, storing energy in vast caverns carved out of salt or rock. And this time, it's not trying to compete with electricity, it's trying to complement it. If it can scale like its proponents think it can, it may be able to solve one of the biggest problems in modern power systems: what to do when the wind isn't blowing and the sun isn't shining. I'm Rosie Barnes, an engineer with 20 years' experience developing clean energy technologies and founder of Partalote Consulting, who provide advice to clean tech startups and investors. In this video, we're going to look at how compressed air went from powering Victoria-era communication networks to being almost completely forgotten, and why it's now being revived as a serious contender for grid-scale energy storage. We'll go through how the technology actually works, the engineering challenges that held it back, and the new designs trying to overcome them. And we're going to look at a real project being built in Australia right now that is converting a disused mine into energy storage. Let's take a trip back a few thousand years or so to see how they used compressed air for energy transfer way back in the Bronze Age. For smelting bronze and then iron, a blacksmith's assistant would get the lucky job of pumping oxygen onto the fire with leather or goatskin bellows to get the fires hot enough for smelting. It must have been a tedious and exhausting job. Jumping over a few thousand years or so to the 19th century, the English inventor George Medhurst inaugurated a dream of using compressed air to help with the logistical and communication challenges of the Industrial Revolution. In 1810, he thought up a revolutionary new way to move things around using differences in air pressure to propel objects through a sealed tube. By either pushing air in behind a container or creating a vacuum in front of it, a container could be shot through a network of pipes at amazing speeds. These were pneumatic tubes. Soon after that, the invention of the telegraph in 1844 brought a huge advance in communication over distance. Wires laid between telegraph stations, including under the sea, allowed the transmission of information and messages via electrical signals entered as Morse code. The telegraph system was very fast, taking only a few hours from sending to receipt. The signals were then reconverted into text at the other end, becoming a telegram. But getting them to their intended recipient could be a lot slower. We see that in old war movies, with the postman on his bicycle, stopping at a house, removing his hat out of respect, then delivering the telegram to the family, which would have told them that their son was killed or missing. Just a decade after the invention of the telegraph, an engineer working in London realised he could use pneumatic tubes to shunt telegrams from one place to another at speed. London's first pneumatic line opened in 1863, with a massive cast iron tunnel built to carry the tubes. Unfortunately, this promising idea faced practical challenges. The tunnel leaked, making it impossible to maintain a vacuum within it, and the project had to be abandoned. Instead, the technology really took off in European cities. In Paris, for example, a 600-kilometre network of pneumatic pipes, known as Le Neu, were suspended from the ceilings of the underground sewer system. They carried small cartridges propelled by compressed air. Heavy maintenance was required, but each cartridge could transmit multiple messages, delivering them to their destination far faster than horse-drawn vehicles could. In the United States, New York, Philadelphia, Chicago, and St. Louis had similar pneumatic systems, which were so effective that in 1900, the US Postmaster General predicted that these tubes would eventually extend to every household for immediate delivery. Why was he wrong? By the turn of the 20th century, the focus had shifted from moving small packages to moving energy itself over long distances. There were 4 possibilities: steam, electricity, water, and air. Steam had been used since the beginning of the Industrial Revolution to drive trains, mills, and pumps, but these applications generated steam on site. Transmission of steam over significant distances, for example to power urban networks, was inefficient, dirty, and dangerous. Hydraulic systems using water could work well locally, especially near fast-flowing rivers, but they required heavy, high-pressure pipelines and suffered significant losses over long distances, making them impractical for large-scale transmission networks. That left electricity and compressed air. Early electricity systems were seen as dangerous and required specialised labour, while compressed air was considered safer and cleaner. But electricity had one advantage that would prove to be decisive: efficiency at scale. When alternating current systems emerged, they could transmit energy over long distances with far lower losses. A 100-mile AC transmission line built in Germany in 1891 achieved around 75% efficiency, far beyond what compressed air systems could manage. And that was effectively the end of compressed air as a serious contender for energy transmission. So compressed air lost the race for energy transmission over distance, but there were many other applications, some of which were taken up by the Parisian company for compressed air in the 1890s. Paris had a pipeline system covering 900 kilometres that delivered compressed air to domestic applications, including apartment blocks, workshops, and institutions where it could power a local generator using the energy stored to run a turbine. Compressed air was also used to precisely coordinate multiple public clocks, over 7,000 of them at one time across Paris. Compressed air was even used to clear out the below-ground foundations of the Eiffel Tower. The underground system for conveying telegrams spread to all sorts of other uses. My mum can remember how in the 1950s, the shop assistant in a big department store would put your invoice and money into a special tube and disappear it into the shop-wide system of tubes under the ceiling. And after a few minutes, your receipt would come shooting back through a system in its own little tube from some distant and invisible office, all powered by compressed air. And after the 50s, compressed air continued to be used, as it still is, for many applications that don't require transmission over long distances, such as drills, nail guns and jackhammers, air brakes and sandblasting, even in roller coasters to operate safety equipment such as brakes and safety restraints. We're used to those applications now. But using compressed air to store electricity is a much more recent idea. Since electricity won the competition for energy transmission over distance, and with the development of variable renewable energy sources like wind and solar, we now need robust storage to make sure that electricity is available when and where we need it. The first patent application for using compressed air as an electrical energy storage medium was issued in 1948 to Fraser W. Gay in the US. Gay's proposal established the fundamental mechanics of modern compressed air energy storage, CAES. First is the charging phase, using inexpensive off-peak power from baseload generation to drive an electric compressor. Second is the storage phase, pumping that compressed air into a dedicated underground chamber. And third is the discharging phase. During peak demand, the pressurized air is reheated and expanded through a turbine to drive an electric generator. The basic activities of charging, storage, and discharge take place via three components: a compressor unit, a storage reservoir, and an expander or turbine that uses the potential energy released from the stored air to run a generator to reproduce electricity for the grid or a specific load. This is a simple enough working mechanism, but to make it cost-effective, some tricky challenges needed to be solved. One of the interesting things about compressed air energy storage is that it's really a system for managing pressure. When there's excess energy on the grid, air gets compressed and stored underground, and later that pressure gets released in a controlled way to generate electricity. Humans aren't that different. We deal with pressure too. Deadlines, work, life. And if we just keep compressing it without any kind of release, things eventually stop working very well. This is where therapy can help, and this video is a paid partnership with BetterHelp. I'll be honest, working on this YouTube channel can nudge me towards burnout faster than you might imagine. There was a week recently where I felt like everything piled up at once. I was trying to finish a script, deal with travel logistics, and keep up with my consulting work. And I just got to the point where I couldn't focus properly on any of it. And I felt like I was busy all day, but not actually getting anything done. That was the point where I realized I couldn't just keep pushing through and expecting it to sort itself out. Having access to a therapist I can speak to regularly has been really helpful. BetterHelp makes starting therapy straightforward. You take a short quiz and quickly get matched with a credentialed therapist and communicate however you feel comfortable, whether that's phone, video, or text. Compared to traditional therapy, I found it way faster to get started, and you can get as much support as you need. That really helps when a sudden life stress comes up. You don't want to wait weeks between appointments. If you're interested, click the link in the description or go to betterhelp.com/engineeringwithrosie to get 10% off your first month of therapy. Now back to the engineering challenges associated with CAES. The first is where to store the compressed air. You might think you can just use tanks above ground, but to do that for grid-scale volumes, pressure vessels would need to be really huge and expensive. It really only works out when using already existing underground caverns, which reduces capital costs by a factor of 10 compared to above ground. And it puts this technology in the ballpark of being cost competitive. This underground storage can be salt rock caverns, abandoned coal or zinc mines, aquifers, or artificially excavated hard rock formations. The goal is always the same: a very large, completely airtight volume underground. Where suitable geology exists, salt caverns are often the most cost-effective option. Salt has very low permeability and even self-heals small cracks over time, which helps keep the storage airtight under repeated cycling at pressure up to around 20 megapascals. Salt caverns are typically created using solution mining. An access well is drilled into the salt formation, then water is injected to dissolve the salt. The resulting brine is pumped out, gradually leaving behind a large hollow cavity of the desired size. Compressed air energy storage officially hit the world stage in 1978 with the commissioning of the first commercial-scale plant in Huntorf, Germany, which was 290 megawatts and later upgraded to 321 megawatts. Designed primarily for baseload shifting and providing black start capability for the grid, the facility stores compressed air in 2 underground salt caverns with a total volume of roughly 310,000 cubic meters at pressures ranging between about 5 to 7 megapascals. The system operated on a diabatic cycle. This means that the heat generated during the compression phase is dissipated into the environment. Natural gas must then be burned to reheat the air to temperatures between 550 and 850 degrees Celsius before it can be effectively expanded to produce electricity. And its round-trip efficiency is therefore quite low at around 42% due to the inherent energy losses of the diabatic process. The evolution of CAES is categorized by how the system manages the heat generated during compression. The first generation, as in the Huntorf plant, requires burning fossil fuels during the discharge phase to reheat the air. But later systems capture and store the thermal energy produced during compression, eliminating the need for fossil fuels. Efficiency with these adiabatic systems increases to 60 to 70% from the 42 to 54% efficiency of the diabatic systems. And there's an emerging technology, isothermal CAES, which aims to maintain a constant temperature throughout the cycle using methods like liquid pistons or mist spray coolings to get efficiency even higher. Despite this early promise, very few large-scale CAES systems were built over the following decades. Low efficiency, reliance on fossil fuels, and limited suitable sites kept the technology on the sidelines. But with a growing need for longer duration energy storage as wind and solar penetration increases, compressed air energy storage is starting to see renewed interest, including a project now being developed in Australia. A Canadian company called Hydrostor is investing in CAES with a 200 megawatt, $600 million facility in Australia. The Silver City Energy Storage Centre will be built near Broken Hill, a mining city in the state of New South Wales, and it will be Australia's first large-scale compressed air energy storage facility, capable of powering up to 80,000 homes for a day. The plan is to take advantage of the hard rock geology of the Broken Hill area, which will not need to be lined to prevent leaks. A disused underground mine site near the proposed cavern will be used to access and excavate rock to create the cavern. Compressed air will be stored in a water-filled 280,000 cubic metre underground cavern, 600 metres underground. In a process called hydrostatic compensation, compressed air enters the cavern and pushes the water to a lake above. As the water flows back, it pushes the air back to the surface where it's reheated and drives a turbine to generate electricity. The water means that when energy is needed, all the air from the underground storage can be released through the turbines. Otherwise, some of the air would need to be left in the cavern to avoid creating a partial vacuum. Water also protects the rock caverns from warping and cracking due to stress caused by cycles of pressurization and depressurization. The new facility will take 12 hours to charge a system and 8 hours to discharge, giving it a round-trip efficiency of about 66%. So now the modern descendants of those 19th century pneumatic systems are now competing with today's dominant storage technology, lithium-ion batteries. And compressed air does have some advantages. It can store large amounts of energy relatively cheaply where the right geology exists, and it has long lifetimes and very low self-discharge. But it's not a guaranteed success story. It depends heavily on geology and may struggle to be cost competitive against lithium-ion batteries in many cases. But I certainly think it's cool that from shooting tubes under cities to storing energy deep underground, compressed air is having another go. Whether it becomes a major part of the grid or stays a niche solution is an open question. Thanks to the Engineering with Rosie Patreon team and YouTube members whose support makes this channel possible. If you want to support this kind of deep dive energy technology video and get early access to new content, we'd love to welcome you to the team, and you can join us at this link, also in the description. By the way, let me know if you enjoyed the historical part of this video. It's something that I find really interesting, but I'll rely on your feedback if you'd like to see more of that, or perhaps you think I spent too long on it. Thanks to BetterHelp for sponsoring this video, and thanks to you for watching. I'll see you in the next video.